We want to be able to classify our triangles either by side length or angle measurements because under certain names, different properties come through. So we want to be able to recognize the type of triangle we have so we know what properties we can apply. So first let's look at terminology based on angle measurement. So a triangle can be acute, and if you look at each of the angles within the triangle, so always have 3 angles in a triangle, but if all of those are under 90 degrees, then that's an acute triangle. There isn't really any special property in terms of linking the angle measurements with the side lengths. It just would be an acute triangle. Where we would get special properties is with an equiangular triangle. So this is where all 3 of the angle measurements are exactly the same. And a word that comes up in geometry is the word congruent. That just means same measurement. You'll see it come up with like measurements with a protractor as well as measurements with a ruler. If just geometric measurements are the same, we could say they are congruent. Now, a property with all triangles, when we have these 3 angles working together, the 3 angles always have to add up to 180 degrees exactly. And that's a property that I wrote down at the bottom here. The 3 angles of a triangle should always add up to 180 degrees. This is a property that we'll go back to a lot. It helps us solve for missing angle measurements. If we know 2 angles, we can always find the other based on this. Now with an equiangular, we have 3 measurements that are the same. So let's go ahead and give that, like, say that's x. Well, this would also be x, this would also be x, and all of those should add up to 180 degrees. So with just a little bit of algebra, you have 3 things adding up to 180 degrees. So we have 3 of these x values for 180 degrees. If we divide by 3, we'll see x should be 60. And that should always be true. So if we have an equiangular triangle, you'll know the 3 measurements. They'll all be 60 degrees every single time. All right, another thing that comes through here is the side lengths, and it's actually one that we'll define down below here. But if we have an equiangular triangle, if we jump down to our definitions for side lengths, it would also be equilateral. So equilateral is when all 3 side lengths are the same. In terms of notation to denote same side lengths, we use these tick marks. And it's like if there's 1 tick mark there and 1 tick mark there, then they're the same measurement. You'll see it pop up in other ones like 2 tick marks. If there's 2 tick marks on another, those match up with each other. So this symbol just means all 3 of those side lengths are the same measurement or congruent. And when that happens, that means all 3 of the angles are also the same. So we would know the angle measurements of this. Each of those angles would be 60 degrees. And then if we have one of the side length measurements, we'd have all of them because they're all the same measurement. So an equilateral triangle, based on defining it on side length, is the same thing as equiangular, defining it based on the angle measurements. All right. Another one based on angle measurement is right triangles. When you have a right triangle, you'll have a right angle in there. And you'll only ever have one. We'll talk about right triangles a lot when we get to Pythagorean theorem, but a special side length that comes up is the hypotenuse. And when you have a right triangle, you always have this longest side of the triangle, and that has the special name of hypotenuse. And you can always find the hypotenuse in that it's always opposite of your 90-degree angle. So with our 90-degree angle in that corner there, if you just look across, you can kind of imagine if you were standing at the vertex for that 90-degree angle and looked across the way, it would be the side length that isn't touching. It would be the one opposite. All right, and we'll talk about properties of right triangles in the video for Pythagorean theorem. And then an obtuse triangle is where if you're looking at the angles, so you can see there's an acute angle, there's an acute angle. If our third angle was acute, then it would be an acute triangle. But in this case, that third angle is obtuse, and that would make an obtuse triangle. So those are 4 options for how we can define a triangle based on the angle measurements. Now, based on side length, we already looked at this one, equilateral, all 3 side lengths are the same. Isosceles, so that's what this notation is showing, is that this side length has 2 tick marks and that side length has 2 tick marks, so they're exactly the same. So you'll have at least 2 congruent sides. Typically isosceles has exactly 2, and then those are called the legs. So this would be a leg, and then we have the other leg, and then that last side that's a different measurement would be called the base. Now what we have in isosceles triangle, there is a special property that occurs with the angle measurements. Now the angle that comes through with the 2 intersecting congruent sides, that one's just kind of a leftover. There isn't anything special about that. What is special are the measurements along the base. The angle measurement at that base and that base are always the same. So your base angles for the isosceles are congruent. So that's a property that can help if you're trying to solve for angle measurements with this. That can help out in filling in those angle measurements, that those 2 should always be exactly the same. All right, and then our last one is if there's just no congruent sides. We have something happening for that side length, something different for that side length, and something different for that third side length. If none of them are the same, then we just call it scaling. So that's how we can define a triangle based on side length. And then what we already talked about is that property that all of the angles should add up to 180 degrees, and we want to keep that in mind. So let's try out some of these properties. So for this image down here, we're going to work on those definitions. So we're going to define by side lengths and angles. And basically we'll see how those come together. So EHG, I'm just going to highlight our triangle EHG. Or in fact, let's just look at this picture for a second before we start our definitions. So we can see is this side length of 12 here, and we have this side length of 10, this side length of 4. Something we could fill in there is that implies that we have this long side length here that measures a total of 14. Basically, by taking that line segment E to F and that line segment F to G, you would just add those up. We have this side length of 11 here. Then we do have a missing side length in here, this HF. However, that notation there with the tick marks, which we know this one lines up with that 10, that implies this side length over here is also 10. So that notation helps kind of simplify the image so you don't have to write all of the numbers over and over again. If you have same values, you can just use that notation to show it. Now, in terms of angle measurements, something that's happening here, and this picture could have been a little bit better to show this, is I'm going to throw in this notation of that is creating a right triangle there, or it's a right angle, so we have these perpendicular lines coming through, and that'll help out with some of our solutions. All right, now let's start with our definitions. So EHG. So we're going to focus on E to H, H to G, and back to E. So our notation here, every triangle is going to be made up of 3 points. And then this notation here just tells you that you're looking at a triangle. So we looked at angle notation, and if it said angle EHG, that would be something very different from what we're looking at. But this gives us an idea of which triangle we want to look at. So EHG, if we're looking in terms of side lengths, what we can notice is we have a side length of 12, 11, and then EG is that total of 14. So we have 3 different side lengths here. So that would be scaling. Then if we look in terms of angle measurements, we just want to look at this angle, which all I could say about that angle is that it's less than 90 degrees. So that would be an acute angle. This angle would also be acute, and this angle would also be acute. So if we have these 3 acute angles, then we call this an acute triangle. So that would be how we define EHG, would be scalene and acute. All right, let's look at this triangle FHG. Let me just clear out some of the piece that I drew there. All right, FHG. So I'm going to connect F, H, and G. So I'm going to have this small triangle over here. All right, in terms of side lengths, my side lengths are 4, 10, and 11. So those are all completely different. So that would be scalene. In terms of angle measurements, well, I have an acute angle there, and then for this angle at F, well, some things that are coming through here, and maybe you can visually just see this, but we have this straight angle, and then we have 90 degrees taken up, and if there's 90 degrees on one side, there's 90 degrees on the other side as well. So this right here is going to be a right triangle. All right, and then our last one is EHF. EHF is coming through right here. Okay. So with EHF in terms of side lengths, we have 10, 10, and 12. So with our side lengths, this would be isosceles because we have two side lengths that are the same at 10. And then in terms of angle measurements, we have a right angle and two acute angles. So this is going to be a right triangle. All right, so that's how we would use those definitions and be able to tell how would it be defined by side length or angle measurement. All right, this last one here, I just want to practice some concepts talked about, like if we know how to classify it, what are some implications of that? Something you might see pop up in homework and in general with geometry is them throwing in this, the figure is not drawn to scale. And basically it's telling you don't really trust your intuition in terms of the lengths and angles that you're seeing in the image, just rely on the numbers. And in fact, this one is going to actually look a lot different than how it's appearing, but I want us to think about just the math side of it, and then I'll draw you a picture for how it would more accurately be presented. So with this, what we can notice is we have a side length of 14 inches, side length of 14 inches. So we have these two sides that are the same here, and then they don't tell us anything about BC, so what we're just going to assume is that it's a different side length. If it was the same side length, they would tell us. So what we want to use is the fact that they're giving us an isosceles triangle. And what I want to find in this is the missing angle measurements. In terms of missing side length, so like solving for that side length BC, we don't have the tools to do that. We would need some trigonometry, which we are not going to do. So we're not going to solve for the side length, but what we are going to do is look for what is angle A and what is angle C. Now, in terms of what I said with isosceles triangles, so you have your legs and base, and for this picture here, 14s are the legs, and then over here is the base. And what happens with an isosceles triangle is that those base angles, the two of them together, should be the same measurement. So if angle B is 30 degrees, angle C should also be 30 degrees. So we can solve for angle C just because it's an isosceles triangle. Those two measurements would be the same. Now with any triangle, if you have two of the measurements, you can always find the third using the fact that they should all add up to 180 degrees. So what I'm going to do is solve for angle A by taking my total 180 degrees, take out the 30 from angle B, take out the 30 from angle C, and we'll see what's left over, which angle A is going to come out to 120 degrees, which is an obtuse angle, which is definitely not what's being shown there at angle A. That's a very acute angle. So it might be a more accurate picture. Let's see, angle A being obtuse, and then we'd have the same side lengths. And this isn't going to be perfect, I'm doing this by hand, but this would be probably a better representation, with that being 120 degrees, 30 degrees, which is acute, 30 degrees with acute, and then having these same side lengths of 14 and 14. That would be a better picture for what we're seeing with A, B, and C. So just be careful of that. If they say a figure is not drawn to scale, just rely on the numbers and properties to solve. And then what can help is redrawing the picture and making sure it all does line up. But those are some properties of triangles.